Alright, this is going to be an overview of the whole chemical reaction unit, and I'm going to do a little section for each topic, and I'm going to go in the same order as the order on your retest review. So it's different questions but same order, so you can follow along with your review and work on that as you go through the video. First section is balancing equations, and we need to balance equations in order to have the same number of each element on both sides. And so we're going to go through and do a few examples. So I'm just going to go one element at a time. I'll start with K. And if you look on both sides of the equation, on the reactant side and the product side, you have 1 K on both sides. So K is balanced. It's the same amount. Next one is Cl. And again, you have 1 Cl on both sides, so it is balanced. Your last element is oxygen. You have 3 on the reactant side and 2 on the product side. Whenever you have 3 and 2 of something, you're going to need to make it to 6. And you can only, when you're balancing, you can only add coefficients. So for example, I cannot change this number because that's the subscript. I have to add a coefficient, which is a big number in front of the whole compound. So if I need to make it to 6, I'm going to put a 2 here because 2 times 3 is 6, so that means this side has 6 oxygen. Because I have 6 oxygen, I need to make sure I have 6 oxygen on the product side. Here I'm going to add a 3 as my coefficient because 3 times 2 is 6. Now if you look back, that 2 also on your reactant side, that 2 affects your number of K and your number of Cl. It's giving it 2 Ks and 2 Cls, so I have to look on the product side. I need 2 Ks and 2 Cls. So if you look now and you do a T-chart, a reactant and product chart, reactants are K, Cl, and O. Products are K, Cl, and O. On your reactant side, you have 2 Ks, and product side, you have 2 Ks. Reactant side, you now have 2 Cls. Product side, you have 2 Cls. Reactant side, you have 6 Os. Product side, you have 6 Os. And so because those numbers are equal, that means that now your equation is balanced. Moving on to question number 2. When you have a polyatomic ion on both sides, we're going to count it as one entity, one thing. Instead of separating it into nitrogen and oxygen, we're just going to count it as a nitrate. And you can do this if you have the same polyatomic on both sides. So again, going one at a time, Pb, you have 1 on the reactant side, 1 on the product side. Nitrate, you have 2 on the reactant side, and you have 1 on the product side. You have 1 NO3. So 2 on the reactant, 1 on the product. I need 2 on the product, so I had a 2 there. Now that's going to affect my number of Ks, so I also have 2 Ks, so I need 2 Ks on the reactant side. And then if you look, you've got now 2 Is on the reactant side, and you have 2 Is on the product side. So to double check, you can do a T-chart, reactants and products. Reactants are Pb, NO3 because we're going to keep it together, K and I, and those are also your products. So if you count up on your reactant side, you've got 1 Pb, product side 1 Pb, reactant side 2 nitrate, product side 2 nitrate, reactant side 2 potassium, product side 2 potassium, and reactant side 2 iodine, product side 2 iodine. So these numbers are all equal, meaning it is a balanced equation, and you are done. Moving on to question 3. H2 plus NO gives you H2O plus N2. So H, start with the first one, 2 and 2, that's balanced. N, you've got 1 and 2, so we need to add a coefficient to make that 2. O, you've got 2 and 1. So I'm going to need to make this 2. All right, now let's look. Let's go back to the beginning. H, you have 2, and now you have 4. You have 2H2, so that makes 4 hydrogen. So that means you're going to need 4 on the reactant side. So you put a 2 here to give you 4 hydrogen. If you think that this is done, you can do a T-chart to check. You have H, N, O. Reactant side, 2 times 2 is 4. Product side, 2 times 2 is 4. Nitrogen is 2 on the reactant, 2 on the product. Oxygen is 2 on the reactant, 2 on the product. So your numbers are equal, therefore it is balanced. So again, you are only able to add coefficients. You cannot change the little number, the subscript. And then the last example, Al plus H2O gives you Al2O3 plus H2. So Al, you've got 1 and 2. So we're going to make this 2. H, you've got 2 and 2, so that's fine. O, you have 1 and 3. So if I made this 3, that means my oxygen is 3 and oxygen is 3. That also now changes my number of H. 3 times 2 is 6, so I need to make sure my product has 6 H's. So I need 3 because 3 times 2 is 6. To double check again, make a T-chart. Al, H, and O. Reactant side 2, product side 2. Reactant side of H is 6, product side of H is 6. Reactant side of O is 3, and product side of O is 3. So your numbers are equal, the equation is balanced. The next section deals with types of reactions, and in your review you have to do type and predict the product. So first we're just going to look at the types. You can have synthesis, and that's where you take 2 separate parts and you make 1 compound or 1 product. Decomposition is the opposite, so you start with one compound and you break it apart. Single replacement is always going to deal with 1 element by itself and a compound to make a new element by itself and a new compound. Double replacement is dealing with 2 compounds to start out with, and it makes 2 new compounds. And combustion, biggest thing here is your products are CO2 and H2O. So it's always going to be, if you see that as your product, then it's going to be a combustion reaction. So first, to just classify these 5 examples as far as type. Number 1, products are CO2 and H2O, so you know that has to be combustion. Number 2, you've got a compound and an element by itself. So if you look up, element by itself in a compound is single replacement. Number 3, you have 2 compounds that you're starting with, and when you start with 2 compounds, it's going to be a double replacement. Number 4, you start with something and you break it apart into 2 pieces. So if you're breaking something apart, it's going to be decomposition. And the last one, you start with 2 pieces and you make 1 product. And so you're building it, you're making a, or synthesizing it, so it's synthesis. So those are your 5 types. When you're predicting products, there's a few more steps involved. First thing you need to do is identify the type. Second thing, you need to make the products. Third thing is balance. So first thing we need to do is identify the type. So you've got 2 parts, 2 separate things. So the only thing you can do to this is combine them into 1 compound, and that type is synthesis. Second one, you have a CH something plus O2, and so if you look back at the example of combustion, those are always going to be the reactants for combustion, and so that type is combustion. Number 3, all you have is a compound, so the only thing you can do to that is separate it or break it down, which would be decomposition. Number 4, you've got a compound and a compound. And when you have two compounds, the type is double replacement. And then the last one, you have a compound and an element by itself. And when you have an element by itself, it's going to be single replacement. An element by itself and a compound. Now we have to go back and predict the products, or make the products. So K plus O2, and you know it's going to make one compound. A lot of people want to just write KO2, and that is incorrect. You are not going to bring the subscript over. What you need to do is you need to look at your charges and crisscross if necessary. So our compound is, we know it's going to be K and O. The charges from the periodic table, K is a +1, O is a -2. Those do not cancel out, so we have to crisscross. The 2 comes down, and the 1 would come down. So once you crisscross, your compound would be K2O1, but remember we don't ever write 1 as a subscript. So your product here, K plus O2, makes K2O. Then if you look back, you can tell that that's not balanced. You have 1 K on the reactant side and 2 on the product side. So we want to balance this by putting a 2 there. You've got 2 oxygen and 1 oxygen, so we need to put a 2 here, which is going to change our K now to 4. So we want to make that 4K. 4K plus O2 gives you 2K2O, and that would be the final answer. Number 2, a combustion always has product CO2 plus H2O. So that's always going to be your product, and we're not going to balance it because I'm going to do an entire little section on balancing combustion reactions. But know that that is not balanced. You would have to then go and balance it. Number 3, you have a compound. We said it's decomposition, so it's going to separate out into Ba and O. From here, you have to think back to Dr. Brinkelhoff, or those 7 elements that are diatomic. It's BRINCL, HO, and F. So because O is part of Dr. Brinkelhoff, we have to put an O2. If you realize now that that does makes it unbalanced, so we would need to put a 2 here and a 2 here to balance the equation. Number 4, we said, is double replacement. So the 2 front parts are going to switch places. That's what happens in a double replacement. So zinc is going to switch places with hydrogen, and so zinc is going to combine with phosphate, and hydrogen is going to combine with hydroxide. Why I wrote it up top is because we have to look at our charges and crisscross to see how they combine. Notice how I said I'm just adding hydrogen, not H3. You don't bring the subscripts over. So starting with zinc and phosphate, zinc is part of the 3-2-1 rule, so zinc is a +2, and phosphate is a -3. So because those don't cancel out, we have to crisscross. So your compound would be zinc with a 3 and PO4. You have 2 of them, and so because it's a polyatomic, make sure to put it in parentheses. Plus H is a +1, OH is a -1, and so those cancel out, so it's just HOH. Now if we go back to balance it, so let me erase this part because that's not in our equation. We just needed to write that to figure out our compounds. You've got 3 zinc on the product side and 1 on the reactant side. I'll do this in a different color because it's getting messy. So you had a 3 there. You've got 6 hydroxide, 3 times 2. So you have 6 OHs. So we want 6 OHs. H is the next thing. You have 3 H's and 6 H's, so I put a 2 here to make that 6 H's. And last part, you have 2 PO4s and 2 PO4s, so that would be balanced. The last one, single replacement, we have an element in a compound. The single element is always going to try to replace the one in front. And so if calcium is replacing hydrogen, that means hydrogen will be by itself. And calcium will be combined with chlorine. Remember, we have to look at the charges. Calcium is a +2, chlorine is a -1. So when we crisscross, you're going to have 1 calcium and 2 chlorines. Also, think back to your Dr. Brinkelhoff. Hydrogen is a part of the diatomic elements, or a part of Dr. Brinkelhoff, so it has to be H2. It can't be by itself. Then to go back and balance it, you have 1 hydrogen on the reactant side and 2 on the product side. Let's put a 2 here. That also gives you 2 Cl's, and you have 2 Cl's on the product side. 1 Ca on the reactant side, 1 Ca on the product side, so that would be balanced. With combustion reactions, there are 2 rules that you have to follow when you are trying to balance them. The first one is if the first carbon is even, start by doubling it. And the second thing is if always balance in this order: carbon, hydrogen, oxygen. So when you're balancing, you always go in that order. First balance your carbon, then balance your hydrogen, then do your oxygen last. What the first rule means is if your number of carbons is even, you start by doubling it, which means put a 2 as a coefficient in front of that compound. So here we've got 1 carbon, so it's not even. And so we can just go through and balance. Carbon, you've got 1 on the reactant side, 1 on the product side. So that's already balanced. Hydrogen, you do next. You have 4 on the product or reactant side and 2 on the product side. So we need to make this 4. So 2 times 2 is 4. And then the last one you do is your oxygen. You've got 2 oxygen coming from here, and you have 2 oxygen coming from here. So you have a total of 4 oxygen on the product side. So you need 4 oxygen on the reactant side. So the ones that have an odd number of carbons to start out with are a little bit easier. Next one we're going to do is if you have an even number of carbons. So if you look at the next example, C2, that's an even number of carbons. So before you start balancing it all, you need to start by doubling this compound or adding a 2. Now we can balance it in the order CHO. So now we've got 2 times 2 is 4. So 4 carbon on the reactant side. So you need 4 carbon on the product side. Next you do H, 2 times 2, so you have 4H on the reactant side. You need 4H on the product side. And the last one is the O's, so let's add them up. 4 times 2 is 8 oxygen coming from here, and 2 oxygen coming from here. That's a total of 10 oxygen on the product side. And so you need 10 oxygen on the reactant side, so you'll add a 5 here because 5 times 2 is 10. One more example of an even numbered carbon one is what I just drew on the bottom. So C6, that's an even number of carbons, so you start by doubling it. Then we can balance in the order of CHO. So 2 times 6 is 12. So you need 12 carbon. H is next. 2 times 6 is 12. So you need 12 hydrogen. Last one is our O's. So you've got 12 times 2, so you have 24 coming from your CO2. And 6 coming from your H2O. 24 plus 6 equals 30. That means 30 oxygens on your product side. You need 30 oxygens on your reactant side, so you add a 15, because 15 times 2 is 30. When you are doing single replacement reactions, you have to refer to the activity series, which is that list on the back of your periodic table. And this is only for single replacement reactions. So the rule here is that your single element must be higher on the activity series list than the element it is trying to replace. So this is, in the first example, Fe is the single element. And so in order for it to replace aluminum, it has to be higher on the list than aluminum. And if you look at your list, Fe is actually below aluminum, so it cannot replace it. So this one is an NR, or no reaction. Next one, single element has to be higher than the one it's trying to replace, and it's always going to be replacing the thing in the front, or the metal. We're actually going to erase this one. Not a good example. Okay, the next one, Ag and H2SO4. So the single element is going to try to replace the one in front, or the other cation. And so if you look on your list, silver is below hydrogen, and so it cannot replace it, so it's no reaction. And last one, Ca is going to try to replace hydrogen. So that means the single element, or Ca, has to be higher than H, and if you look on your list, it is. So it's going to switch places. H is going to be the new thing that's by itself, and we need to make a compound that has calcium and chlorine combined. So this is where you have to look at your charges and crisscross. Ca is a +2, Cl is a -1. So the compound that you make is going to be CaCl2. And then you also have to look, H is part of your Dr. Brinkelhoff, or your 7 diatomic elements, so it's going to be H2. If you want to go back and balance it, you would need to add that coefficient as a 2, and then it would be balanced. This is taking word equations and writing it into chemical reactions. So you're just going to take each word and write it as the element symbol instead of the word. So zinc and lead-2 nitrate. So zinc is just Zn. Let me do it in a different color. Zn and means plus. Lead-2 nitrate, you have to look at your charges and crisscross. So lead-2 means that it's Pb with a +2. Nitrate is NO3 with a -1, and so because those don't cancel out, you have to crisscross. And so your actual compound is going to be what we write, which is PbNO3 2. Yield means arrow. Zinc nitrate, so again we're going to look at our charges. Zn is part of the 3-2-1 rule, so it's +2. And nitrate, again, is NO3 -1. Those don't cancel out, so you have to crisscross. Which, the compound that we need to write is ZnNO3 2, and so we do plus lead, Pb. And notice lead and zinc are by themselves, and they are not part of Dr. Brinkelhoff, meaning they are not diatomic. Next one, aluminum bromide. So aluminum is Al with a +3 charge, bromine is Br with a -1. So aluminum bromide would be AlBr3. And chlorine, so plus Cl. Now remember, Cl is part of Dr. Brinkelhoff, so it's Cl2. These yield, so these arrow. Aluminum chloride, aluminum is a +3, chlorine is a -1, so we have to crisscross. AlCl3. And bromine, so plus Br. And bromine is, again, a part of Dr. Brinkelhoff, so it's Br2. Last thing that we need to do here is balance. So you've got aluminum 1 and 1. 1 and 1. Bromine 3 and 2. And chlorine 2 and 3. So remember, whenever we have 2 and 3 of something, we have to make it to 6. So 2 there is going to make 6 bromine. 3 here is going to make 6 bromine. 3 there is going to make 6 chlorine, and a 2 there is going to make 6 chlorine. And if you did your T-chart, you should see that they are all equal, so they are balanced. Last one, sodium phosphate. So sodium is Na plus 1. Phosphate is PO4 minus 3. So you'd have to crisscross those. So sodium phosphate is going to be Na3PO4. And so we do plus. Calcium chloride, so calcium is Ca plus 2, chlorine is Cl minus 1. So when we crisscross to make our compound, it would be CaCl2, and that's what you need to write in. Yield, so that's your arrow. Calcium phosphate. Calcium is a plus 2, phosphate is a minus 3. We have to crisscross. So your compound is Ca3PO42. And sodium chloride, so plus sodium is a plus 1, chlorine is a minus 1, so your compound that cancels out is just NaCl. If we look, that's not balanced, so Na, you've got 3 and 1, so put a 3 here. Ca, you've got 1 and 3, so put a 3 here. Cl, you have 2 and 3, so now we know we're going to have to make that to 6. So we need a 6. Now let's look to see where we're at. 6 NAs mean we need 6 Na on the reactant side, so I need a 2 here. Let's just restart. 6 NAs, 6 NAs. 2 PO4s, 2 PO4s. 3 CAs, 3 CAs. And 6 CLs, 6 CLs. So that would be balanced. With oxidation and reduction reactions, or redox reactions, there's 4 rules that you need to remember. First one is that any element by itself, the oxidation number is 0. Oxygen always has an oxidation number of -2. A cation always has an oxidation number equal to its charge. So a cation, basically I mean any metal or anything to the left of the staircase is going to have an oxidation number that's equal to its charge. And then the oxidation numbers in a compound add up to 0. So if we look at number 1, any element by itself, oxidation number is 0. So H2, it's not bonded to any other element. It's by itself, so it's 0. Same with O2. Next rule is oxygen is always -2. And a cation is always its charge. So hydrogen is in the +1 category, so hydrogen is a +1. And we have 2 hydrogens, so that's donating a total of +2. And oxygen is donating a total of -2. So if you add those together, that would equal 0, and that is important to make sure that it always equals 0. Next step, what we need to do is figure out what was oxidized and what was reduced. So I like to draw a line connecting the elements, hydrogen to hydrogen and oxygen to oxygen. So if you follow this, hydrogen went from 0 to +1, and oxygen went from 0 to -2. Whatever element was reduced, or the number was reduced, that element is reduced. So you look for the number that went down. Oxygen went from 0 to -2, so that number was reduced. That means oxygen was the element that was reduced. Hydrogen, the number went up, and so because it went up, it was oxidized. So hydrogen was oxidized. Number 2, we're going to start again labeling our oxidation numbers. So anything by itself is 0. So Fe is by itself, and Zn is by itself. Any oxygen is our -2, and we don't have any oxygens. Next, go to your metals, or your cations. They're always their charge, so zinc is part of the 3-2-1 rule, so zinc is +2. And iron, Fe, we don't know the charge of it, but because it's combined with 3 chlorines, and we know chlorine is a -1, iron would have to be +3. Also, that means each chlorine is -1. And on the reactant side, each chlorine is -1, because now look, zinc has a total of +2. And chlorine is contributing a total of -2. And if you add those together, that equals 0. So we know that those oxidation numbers are correct. If we want to double check FeCl3, Fe is total of +3. Chlorine has a total of -3 because you have 3 -1s. That equals 0, so that's correct. Now we need to figure out which one was oxidized and which one was reduced. So you're going to draw lines to only the ones that changed. So if you notice, Cl went from -1 to -1. So this one was not oxidized or reduced. The only ones that changed were iron. It went from 0 to +3, and zinc went from 2 to 0. So you look first for the one that was reduced, the number that was reduced. Zinc went from 2 to 0, so that number was reduced. That means zinc is the element that was reduced. And iron went from 0 to 3, so it went up. That means that it was oxidized. Example number 3. So start by labeling anything that's by itself 0, but we don't have anything by itself. Oxygen, -2, we don't have any oxygens. So now we have to go and do our metals, or our cations. In this compound, SnCl2, in the compound, Sn would have to be +2. So therefore, each chlorine is -1. So we have a total of +2 and a total of -2. Hg would have to be a +2. Each chlorine would have to be -1. So you have a total of +2 and -2. Sn would have to be in this compound a total of, or it have to be +4 charge. Therefore, chlorine is -1. Total of +4 and a total of -4. And mercury, Hg, would have to be +1 in this compound because chlorine is -1. +1, -1. So all, -1. So all of your compounds, the oxidation numbers add up to 0. Now we want to look at which ones changed. Sn went from 2 to 4, so that changed. Hg went from 2 to 1, so that changed. And your Cl's didn't change at all. So you look for the one that was reduced. Hg went from 2 to 1, so that number was reduced. That means that element was reduced. And Sn went from 2 to 4, so it went up. That means that one was oxidized. And the last one, anything by itself is 0. So Al is 0, Fe is 0. Oxygen is always -2. And then the cation, or the metal, is always its charge. We know aluminum is a +3. And if you look to double check, it's Al2O3, so that means 3 times 2, I have a total of +6 coming from here, and a total of -6, so that's correct. total of -6 coming from my oxygen, so I would need a total of +6 coming from my iron. And you've got 2 irons, so each iron has to be +3. To figure out what was oxidized and reduced, we look at what changed. Al went from 0 to 3, Fe went from 3 to 0, and O did not change. So aluminum went up, iron went down. Iron's oxidation number was reduced. That means iron was reduced, which means the other one, or aluminum, was oxidized. The last part is just looking at half reactions, and so all we care about is where the electrons are located. If the electrons in the equation given, if the electrons are on the reactant side, then it means that is showing a reduction, or it's being reduced. So I just remember reactant, reduced. If they're on the product side, that means that they're being oxidized. So in the first example, your electrons are on the right side of the arrow, meaning they're a product. If they're a product, they're oxidized. Second example, your electrons are on the product side, that means it is oxidized. And third example, your electrons are on your reactant side, meaning they're on the left-hand side of the arrow. Reactant means reduced. The last part of the review is true-false questions about evidence of a chemical reaction. These are the notes that you should have over what is a chemical reaction, and then the 5 things that can tell you if a chemical reaction is taking place.